Hi students, welcome to our physics channel, Physics and Me. Okay, today I'm going to explain the topic electricity, on which I have done two classes, two videos. Okay, up to current density I have explained in that. Now I'm going to tell you exactly what is the relation between current density and drift velocity. What is the relation between the current and the drift velocity? First of all, let us know what is the drift velocity of the electron. As in the previous classes, I have already told you. Suppose if we consider a conductor, if we consider a simple wire, in that wire, if we see that in microscopic level, okay, we can observe that. I mean, if we go through the wire in a microscopic level, now we can say that the electrons will be moving inside any conductor. Wire is a conductor, right? So the electrons are moving inside the conductor, and how they move, I have already told in my lecture 1. Okay, in current electricity, you just go through it once, go through my previous lecture so that you can understand them. And now let us discuss what is a drift velocity. What is a drift velocity? Okay, let us discuss what is drift velocity. Drift velocity of an electron. See, what is a drift velocity? Now, we have discussed a story in the previous lecture that suppose if wire is there, suppose if we consider a wire, assume that this is a wire. Now, I'm showing that in microscopic level. I'm showing that in microscopic level, okay? This is a wire. In that, now I'm taking one electron. This is the electron. It resides at this position. Now, how will be the electron? Actually, the electrons in the conductors are loosely bound to the nucleus. Am I right or not? Loosely bound to the nucleus. Why? Because they have much energy. Okay. That's why they are called as free electrons. They can move in random manner throughout the conductor freely. Throughout the conductor freely. They can move throughout the conductor freely. So when an electron comes out of the atom, when an electron comes out of the atom, then the atom gets positively charged. Obviously, am I right or not? Initially, any atom consists of equal number of electrons and protons. How many number of electrons are there outside the nucleus? The same number of protons are there inside the nucleus also. So that's why initially each and every atom is neutrally charged. Whenever an electron comes out of it, then automatically it loses the electron. That's why it gains positive charge. It gains positive charge. And that positive charge, I've already told you in the previous lecture, that positive charge is called as a kernel, or it is also called as a lattice. Means atom. Okay, now that atom which gains the positive charge is called as a lattice. So whenever these electrons are coming out of the atom, then automatically they will be moving here and there like in random manner. So when they move in random manner, then obviously we can say that there is no actually any energy source to the electron. Is there any energy source? There's nothing. But the electron is gaining certain energy and it is moving. It is gaining kinetic energy. From where it is gaining kinetic energy? We have discussed that the electron is gaining the kinetic energy, okay, from the outside atmosphere in the form of thermal energy. In the form of thermal energy, the electron gains a certain kinetic energy. Okay, due to thermal energy, it gains the energy and it is moving in random manner. So in such cases, the average velocity of all these electrons will become zero. The average velocity of either we can take one electron in a particular time interval delta t. In a particular time interval delta t, if we consider the average velocity, then it will be zero. Or if we consider the average velocity of number of electrons at a time, then even then also it will be zero. That is, before we are connecting any wire to the external power source or external battery. Okay, so before that, whatever is happening, I have explained now. Then after connecting the wire to a battery, then what happens? Then what happens? The electron still, does it move in straight path? No, even now also. Even though if it is connected to the battery, the electron will move in random manner only. The electron will move in random manner only. Something like this. The electron will move in random manner only. Okay. Then what is the difference? See here, while the electron is moving in random manner, it will have a specified path. It has a targeted path. Means it has to go from negative to positive. Initially, it was not like that. Yes or no? Some electrons will go from left to right, and some electrons will go from right to left. Like that, it was happened initially when we don't connect it to a battery. But now it is not like that. When we connect this wire to a battery, then automatically these electrons will move here and there, even now also. But the thing is, they'll have a targeted path. They'll have a target. What is a target? Inside, whenever we connect the wire to a battery, the electric field will be set inside the conductor. The electric field will be set inside the conductor, and that electric field is from okay, that electric field is from positive to negative. This is a direction of electric field. This is the direction of electric field inside the wire, inside the conductor. So that's why what happens when electric field is set inside the conductor, then what happens? Electrons will be attracted towards the electric field. Means in the opposite direction, in the opposite to electric field, in the opposite direction of the electric field, the electrons will move like this. Means the electrons will get accelerated. Got my point? The electrons will get accelerated opposite to the direction of electric field. If we consider positive charge, then those positive charge will accelerate in the direction of electric field. It is conventionally. Okay. So these electrons, now they have set a target. Now they have set a target that they have to move opposite to the direction of electric field. They have to move opposite to the direction of electric field, means in this direction they have to move. If they want to move in this direction, you know what happens? It's a very interesting. Okay, whenever they come out of the atom, then automatically it is what we call a lattice. Am I right? I already told you that. We call it as a lattice. So that lattice, suppose if there is a lattice at this position, okay, now lattice means positive charge. Now if this electron is trying to move opposite to the direction of electric field, immediately what happens? This lattice is positively charged and this electron is negatively charged. That's why it attracts that electrons. It attracts the electron. That's why what happens? It goes and attracts to kernel or lattice. This electron will go and attracts to lattice. Will it go slowly? No. Because of that electric field which is set inside the conductor, it accelerates and it goes very fast. And there it collides with the lattice. It does not go slowly. It goes fast and it collides with the lattice. Okay. So first it accelerates. It accelerates and it collides with the lattice. It collides with the lattice. Why? Because of attraction. Because of attractive force. Got my point on it. Again, there is one more. Then what happens? See here, a target is set for it. A target is set. Okay, now what is a target? The electric field is pulling, that means electron has to move opposite to the direction of electric field. Force acts on it. Okay, if the field is acting on it, what does it mean? It means that the force is also acting on it, right? So due to that force, again it tries to accelerate opposite to the electric field. Means it tries to remove the bonding from the atom, from the lattice. Okay, now then again it comes out of the lattice and again it moves opposite to the direction of electric field. It accelerates. Certain force acts on it. What is that force? That force F is equal to, that force F is equal to, I'm sorry, EQ. Because already in electrostatics we have discussed about this electric field. Electric field is equal to F by Q, force acting per unit charge. Then what is this force? Force F is equal to EQ. Means here we are talking about only one electron, that's why I'm writing it as E into small e into E. What is small e here? Charge of one electron. Okay, now. So this is a force applied on a single charge now. So due to that, what happens? It accelerates. Due to that, it accelerates. Assume that the mass of the electron is m and the acceleration is a. Therefore, according to Newton's second law, we write it as F is equal to m into a. Therefore, a is equal to what is the acceleration of it? Therefore, we can write it as E small e into capital E by m. This is the acceleration of the electron, which travels opposite to the direction of electric field. Do you understand? Now, is it going in a straight manner opposite to the direction, exactly opposite to the direction of electric field? It is not like that. Then what happens? Meanwhile, while it is traveling opposite to the direction of electric field, meanwhile, all the lattices are there. So many lattices are there inside that conductor. What do? They used to attract these electrons continuously. So what happens? First it accelerates and it goes and it collides with that lattice and comes to rest. Immediately what happens? Force is continuously acting on it. So due to that, again it accelerates. Okay, now when it accelerates, again one more lattice attracts that. Then again what happens? It goes and again it hits another lattice and again it comes to rest. And another again a force is acting continuously on it. Continuously a force is acting on it. That's why what happens? Again it comes out of this lattice and again it accelerates. Acceleration, collision, coming to rest. Acceleration, collision, coming to rest. This is the thing which happens in the case of an electron inside the conductor. So in between two successive collisions, in between, see, first it collides with this particle and later it collides with this particle. So it is a first collision. Let us assume that it is a first collision and during the next collision. So between the two successive collisions, it might have covered an average distance with an average velocity. It might have covered the distance, certain distance. See here, assume that this is when it collides for the first time. This is when it collides for the second time. Okay, now, then there will be a distance between these two. There will be a distance between these two. See here. See here, there is a distance between these two. Am I right or not? What is that? I mean, there is a displacement in between these two successive collisions, and that displacement is opposite to the direction of electric field. The displacement is opposite to the direction of electric field. Yes or no? Yes or no? Between two successive collisions. And the time taken between two successive collisions is called as relaxation time. Relaxation time means until it relaxes. The time until which it relaxes, it moves in a relaxed manner. Okay, without any collisions. If there is no collision, it means that it is relaxing. No? So the time taken in between two successive collisions is called as relaxation time and it is denoted with the letter tau. Understand? And also it might have covered certain distance L. It might have covered certain displacement L, so that we can write it as with how much acceleration? With E into capital E by small m. With this much of acceleration, it moves. Meanwhile, it covers L distance, which we call it as mean free path. Okay. And meanwhile, the time taken between two successive collisions, we just call it as, what do we call? Relaxation time. So in between two successive collisions, now if we consider the motion of the electron, it is not in random, I'm sorry, it is not in ordered motion, it is in random manner. Understand? So that's why still we can say that, its motion is not in ordered motion. Even though we are connecting it to a battery, its motion is not ordered motion. It is random motion only, but it has a specified path. It has a specified path. It has a set a certain target. It has to go from negative to positive. It has to go opposite to the electric field. It has set a target. Got my point? Okay. So that velocity, that average velocity is called as drift velocity. And this type of motion is called as drift motion. Drift motion. See, I'll tell you a simple example. A student is there who walks in a random manner by playing with a football or something else. By playing with a football, a student is going from uh, school to house by playing with a football. Okay, he does not go by in a straight manner. Am I right or not? He just hits the ball here and he just hits the ball here and there. Okay, now like that he used to go like this in a random manner. He used to go, but definitely he'll reach. Definitely he will reach from from school to house. Definitely, but not in a straight manner. He used to go in different manner, in a random manner. That type of motion is called as drifting. Here we used to call this type of motion as drift motion. Drift motion is completely different to that of random motion, a normal general motion. Drift motion means it moves in a random manner, but the path will be specified. There is a target for it. Understand? So drift velocity is denoted by the letter Vd. Drift velocity is denoted with the letter Vd here. And L can be written as here. L can be written as, if it is moving with a particular acceleration, we can write it as, according to kinematics, we can write it as half at square. What is this t here? Relaxation time. Hence you can write half into, what is a? E into capital E by small m into tau square. This is L. This is a displacement that an electron has traveled. This is a displacement. Okay, this is a drift velocity. Okay, now let us consider that this is drift velocity can be written as L by tau, because displacement by time taken, very simple, average distance by time taken. Okay, then we can write it as half into E by m into tau square by tau. Hence you can write it as Vd is equal to 1 by 2 into E by m into tau. Okay. Now let us write this in a proper manner so that you can understand what is this. Vd is equal to, now I'm writing in a proper manner, E tau by 2m into E. Why I am writing like this? Why? Because E is constant. E is nothing but the charge of the electron. It is constant, 1.6 into 10 power minus 19 coulombs. And the tau is relaxation time. That is also constant for a particular, this one, a particular conductor, right? And 2 and m is also constant mass of the electron. So this total term is constant. E tau by 2m is constant completely. That's why we are writing here. This is electric field. Therefore, we can write it as Vd is directly proportional to E. What do we understand from this? From this relation, we can understand that if we increase the electric field, automatically the electron moves fast. Very simple. Am I right on it? The electron gains more drift velocity. If electric field is more, very simple to understand. If force is more, automatically that object will move with a greater acceleration, or that average velocity will be greater. Am I right on it? Even here also, electric field is nothing but force only, So if the electric field is greater, then automatically the drift velocity also increases. If the electric field is less, drift velocity also is less. Okay, now that is VD is proportional to E. This is a relation between VD and E, electric field. Understand? This is about drift velocity. This is about drift velocity. And now let us discuss about the relation between drift velocity and current, and the relation between the drift velocity and current density. Okay. So here now let us discuss about relation between current and electric current and drift velocity VD. In order to find out this relation, first of all, now I am assuming a conductor. I am assuming a wire. In that, I'm taking a certain volume of that wire. Okay. I've taken the cross-sectional area at two different points. At two different points, I'm taking the cross-sectional area. So in between these two cross-sectional areas, a certain volume is there. No. Now, what is that volume here? What is the volume of this conductor? Volume V is equal to volume of this conductor. Now let us write it as volume of this conductor V is equal to, we can write it as area into length. Why? Because it is in cylindrical shape, right? So what is the volume of this? What is the volume of this cylinder? It is nothing but A into L. Okay. And when the electron travels in this length, with what velocity it travels? Obviously, previously we have discussed that it travels with a velocity called drift velocity. Am I right on it? So suppose if it takes t time, within t time interval, it is going from this point. Let us take this point as P and let us take this point as Q. So within this time, within t time interval, the electron is going from P to Q, means it is covering L distance. So therefore, this volume can also be written as A into, instead of length, I'm writing it as drift velocity into time taken. Okay, drift velocity into time taken. Right? So drift velocity into time taken, which is nothing but distance distance is equal to speed into time. No? So we can write it as VD into T. Yes. So this is volume. So within that much of volume, how many number of electrons are going? Within that much of volume, how many number of electrons are going? Therefore, the total charge which is passing through that, the total charge passing through the wire, the total charge passing through the wire, that is capital Q is equal to, total charge means what? Means in that total volume, how many number of electrons are there, that we have to calculate. So the number of electrons are N into E. The number of electrons are N into E. And what is the total volume in it? Total volume is A into VD into T. Means what is the total number here? Total charge by, okay, per unit volume we have to consider, no. So that's why we are considering it as Q is equal to N E into number of electrons into the total volume. Okay, now that will give you the total amount of charge which is passing through. Here, only one electron will not be there inside the conductor, right? So there will be so many number of electrons, so many number of atoms, right? So those many number of electrons are passing while they are passing with a drift velocity VD inside that conductor to a distance L. Then we can write that total charge Q is N into E into A into VD into T. within t time interval. Then what is the current? Therefore, the current produced in it. Therefore, current produced within time t inside that conductor, within time t inside that conductor. How do we calculate? I is equal to, as we already know that it is q by t. Am I right on a total charge per unit time, right? So therefore, what is q here? N into E into A into Vd into time t by time t, time interval. So therefore, tt gets cancelled. What do we write? N E A Vd. This is a relation between the current and drift velocity. This is a relation between the current and drift velocity. See here. Understand? This is a relation between the current and drift velocity. I is equal to NEAVD. So here, if you observe that carefully, depending on what factors does I value depend? Okay, on what factors does I value depend? See, you can directly say, see, if electric field increases, you know what happens? Previously we have done, see here, previously, this is a previous one. If the electric field increases, then what happens? Drift velocity increases. Am I right or not? If the drift velocity increases, then what happens? Current increases. Yes or no? Why? Because N is a number of electrons per unit volume, that is number density, right? Density. Electron density it is. Okay. E is charge, that is also constant. Capital A, area of cross section of wire, even that is also constant for a particular conductor. Then Vd only changes when electric field increases, drift velocity increases. When does the electric field increase? When potential difference, when we are connecting it to a battery, when that voltage increases, or when that external source, suppose general battery if we consider, then what is its what is its voltage? It will be 1.5 volts. If you can observe that, it will be written on the battery itself, 1.5 volts. Okay, now if we just increase that, then what happens? Potential difference, V value increases. If V value increases, then automatically current also increases. I mean, how does it increase? If V value increases, then E increases first. Electric field increases. If E increases, Vd increases. If Vd increases, then current increases. There is an interrelation between all these terms, right? Now let us send this A to this side, to the left side, so that it will become I by A is equal to NEVD. What is I by A? We can write that I by A is called J, current density. In the previous class, in second video, I have explained about the J value, current density, right? So J is equal to NEVD. Now this is a relation between J, current density, and drift velocity. This is a relation between the current density and drift velocity, right? Okay. So Vd, what is a formula for Vd? What is a formula for Vd? If once we recollect it, right? Vd is equal to E tau by 2m into E, right? So therefore, now let us write the same thing here. J is equal to N into E tau by 2m into E, right? Now see here, J can be written as N E square tau by 2m into E. Now observe this carefully. From this, we can say directly that J is equal to this total term n e square tau by 2m. N is nothing but density of electrons, E is nothing but charge, tau is relaxation time 2, and m is mass of the electron, and everything is constant in this. So all these total terms, now I am naming it as sigma. Why? Because sigma is a constant. Okay, now into E here. Therefore, from this we can write J. J is equal to sigma into E. You know what? This is the actual form of Ohm's law. This is the actual form of Ohm's law. Okay. Now let us discuss how it is. See here, J means what? You just observe, imagine once. J means what? The current flowing through unit area is called as current density. Am I right or not? So if that increases, what does it mean? It means that electric field is increasing. If electric field is increasing, what does it mean? It means that we are giving more potential difference to it. Got my point on? Therefore, everything is interrelated, as I have already told you now, so that it is very simple to understand. J can be written as I by A, right? Current, obviously, it is related to current. So, if electric field is greater, if electric field is increased, then current density also increases. This is the actual form of Ohm's law. This is the actual form of Ohm's law. Understand? So from this, we can write it as I by A. J place in the place of J, I'm writing I by A. Okay, now why? Because current density is I by A, right? A is equal to sigma. Sigma, I'm writing it as 1 by rho. Sigma is called as conductivity. Later, I'll tell you that sigma is called conductivity, and I'm writing it as 1 by rho. 1 by rho is called as resistivity into E. I'm writing that in terms of potential difference, that is V by L. I'll tell you what is potential difference, and in the already you might have observed that in electrostatics, what is meant by electric potential and potential difference, right? So that V by L we can write. There is a relation between the potential and electric field, electric potential and field. That can be written as E is equal to V by L. Actually, we have to write it as dou V by dou L. Now I'm writing it as V by L. We have to assume that these are all small values. So therefore, we can write it as V is equal to, okay, V is equal to rho L by A into I. That's why we are writing it as V is equal to I. And this is an actual form of Ohm's law that we are studying. Okay? This is the Ohm's law which we are studying. V is equal to Ri. What does it mean? It means the potential difference. V means it's not potential, it is potential difference. Okay. Well, let us write it as delta V, no problem. Delta V is proportional to I. Delta V is proportional to I. This is Ohm's law. This is Ohm's law. Do you understand? So this is about Ohm's law, and this is a relation between current and drift velocity, and the current density and drift velocity, and from that we are deriving Ohm's law now. Slowly. Am I right? Now let us do some problems regarding these relations. Okay, and later I'll explain you what is Ohm's law exactly in our next topic. next video. Thank you all. Okay, keep watching and just follow my lectures. Definitely you'll understand the conceptual knowledge. You'll get the concept, you'll gain the conceptual knowledge definitely. And subscribe and just press the bell icon so that you'll get the notifications of my videos whenever I do. Okay, so keep watching. Thank you all.